Here's a demonstration of the recurrence that I was talking about in the little thing I sent out, and I want to show you how this works. So first, let me show you one of the examples I talked about where we have a minute hand that moves 1.5 times the speed of the hour hand, and we'll see what happens with that. So the red X here is the hour hand, and the green O is the minute hand, and now it's gone once around. Let me start that again, actually, now that you get an idea that the inner circle is the hour hand, the position of the outer hand, and the outer circle is the position of the minute hand. And let me start it again. And the green circle is the minute hand moving around half again as fast, and now the hour hand has gone around exactly once, and I've paused it. And the blue circle at the bottom indicates one of the positions in this set S that I was talking about, of all the positions that you can find the minute hand at when the hour hand is at 12. And now we'll let it go some more, and we see that when the hour hand gets back to 12, we've gone exactly back up. And so that's because it's a rational number. We actually just nail exactly back. They're both exactly vertical again at the 12 position. But if we keep going, nothing else interesting is going to happen with this thing. One more hour later, the minute hand is at the bottom, and it's just replicating the blue circle on the bottom. And yet another hour later, they're just both up at the top. And that's all that happens. Another example that I was talking about was where it's 4/3. The ratio of the speeds is 4/3. Here, after 1 hour, the blue circle now is at the 4 o'clock position, 1/3 of the way around the wheel. Then you continue, and the green circle at the tip of the minute hand goes around, and after 1 hour later, you get another blue circle, and that's where the minute hand is on the hour. At 2 o'clock, it's at the 8 o'clock position. And then, again, if you do 1 more hour, as I noticed in the handout, you get exactly back, so they're both at 12. Again, because the R was a rational number. And now if you keep going, it just repeats that pattern exactly over and over again. So that's what happens when the ratio of the speeds is a rational number. You get a certain finite number of equally spaced places where you can find the minute hand on the hour. Those are the blue circles, and that's all it's ever going to do. Now let's look at the case where it's an irrational number. So here the ratio is, I think I picked the square root of 1.1. And so it's just a little faster. The green is just a little faster than the red. And now after 1 hour, it's gone around just a little bit more than one time around the minute hand. And I'm going to put a blue circle there. And now it's racing ahead a little bit again. And at the top, I've got a black circle to indicate that's where they both started at 12. That's the 12 o'clock position. That's where it started. And the question is, will it ever get there exactly again? After 2 hours, it's a bit ahead, and it's put another blue circle. And there's another blue circle at 3 hours. And it's going to keep making these blue circles, and those are all the positions that we find the minute hand at when the hour hand is in the right position at 12 o'clock. And the question is, are those blue circles going to come around and exactly match up with the black circle? Because each of them is an irrational fraction of the circle, the answer is absolutely no. So let me kill this version and go to a faster version. So I'm just running it a little faster, putting in these circles. So each time it pauses, that's another hour on the hour hand, and the minute hand has going around once and a little bit, square root of 1.1, in fact, of a full revolution. And so we see that it's filling out a regularly spaced part of the circle, but that regular spacing doesn't fit in perfectly into the circle. And so what it's doing, it doesn't come back to where it started, not yet anyway. It's not a proof that it never will, but the proof that it never will is based on the mathematics, not on the experiment. And here it keeps going, And what's it going to do? This one, it happens to be, this demonstrates one of the things I was saying about recurrence, is it's not going to actually get back to exactly where it started. But it actually comes pretty darn close. You can see those circles overlap. So one way to interpret these circles would be, if the width of the circle is the accuracy to which I can measure things physically, then in fact, to within well under that accuracy of measurement, this thing has started to repeat itself. And those circles, since they're all overlapping, they're pretty much as to that accuracy, they are repeating themselves. Now, if you could measure with better accuracy, it's not. We can see that the circles aren't exactly the same. And so it really depends on what accuracy of measurement you have, whether or not you judge this to be recurrence or not. And as you can see, as it keeps going, it starts filling out those circles. Now, what's going to happen eventually, you can see that those circles are a little bit offset. It's going to start filling out more and more and more of the circle. And we don't have time to fill out the whole thing, but eventually it would all just be completely covered with blue circles, because every point can be approximated arbitrarily well after an arbitrarily long time by these circles. And in fact, then they'll start repeating over and over again and just getting denser and denser and denser.